Okay, so today there's going to be two lectures. We have a makeup lecture. We are in the chapter of the course, which is on interacting systems. And last time we talked a little bit about how the interaction potential enters into the statistical mechanics. And we talked about a little bit of intuition about how interactions can change the equation of state. And I gave you a very sort of superficial hand-waving argument for one sort of equation of state that you may obtain, and that was the van der Waals equation of state. So today I want to do the systematic way of doing a many-body theory. Hang on a second. Yeah, you have a question?
She wrote on the question, just on the exam papers.
Hang on, wait 1 second. Wait 1 second, please. All right, so what we're going to cover today is a very nice way to do the interacting particle problem, which I will use the virial equation of state, and then I'll tell you about 2-point correlation functions and the second virial coefficient, and then a very systematic, the most systematic way to do many-body theory, which was developed by Mayer, who is one of the mayors for whom this building is named after. So you'll get to find out what they did. Then we will have a continuation lecture after this lecture, which will discuss how the theorem breaks down, how the systematic method fails, and we will talk about charged fluids and tell you about a really interesting way of dealing with charged fluids, which comes from amine field theory and is known as Debye-Hauke theory. So let's get started. So I want to remind you of the quantity called the virial that we defined. We defined it a lecture or two ago. So it's some curly v, which I'm not very good at writing, and it was defined to be the following: the expectation value from I equals 1 to 3n qi pi dot, where qi are the coordinates of the particles and the pi's are the momenta. And the virial theorem, which we derived from the equipartition theorem, told us, the generalized equipartition theorem, told us that this thing has to be equal to minus 3n kbt, and this is an exact result. So why this is going to be interesting is I'm going to show you that this quantity enables us to compute the pressure of a gas in terms of how much the particles affect each other. So that's going to be in terms of a thing called the correlation function. So let's think about the background of this. So in last lecture, I told you about the van der Waals equation of state, and as you can see on the left-hand panel, what you can see is that the pressure in an interacting gas is reduced near the walls because the particles are banging into the walls, but there's long-range attractive interactions between the particles, and so that's going to pull them back, and so therefore the pressure at the wall, which is the force per unit area, is going to be reduced from what it would be for the ideal gas. So what that means is that the pressure then is somehow related to how the particles are pulling each other back. So when the particles interact and the ones in the bulk attract to the middle of the container, in fact, to the middle of a container, the particles that would normally be at the wall so the particles, so our picture is, here is our box, and then here are our particles bouncing around inside it, and then so they have some uniform distribution if the particles are non-interacting. But now let's suppose I color the particles near the wall in purple, and these particles are ones that if I were to amplify what I see near the wall, so here is the wall, what I would be seeing is one of these, this particle here would be coming in and bouncing off the wall and coming back in the other direction. So this is the type of interaction that causes the force on the wall of the container and therefore affects the pressure. So now what's going to happen is that the yellow ones inside the bulk, they're pulling backwards this particle, so we can think of it as experiencing a force in this direction. And because it's experiencing a force in this direction, that means that the pressure is reduced. Now, if this here were an ideal gas, then there'd be a uniform distribution inside it. But now when I turn on interactions, then that means that the density will vary due to the, well, that's not really a very good statement, is it? The density near the wall is reduced by the long range attractions. And so that means that the density of particles is not just a constant. And so and it will depend on how likely it is that there is a particle pulling nearby to pull back the particles near the wall. So I'm giving you this long-winded verbal explanation because I want you to get some feel for why it is that therefore that the pressure is going to be depending on the correlations, the statistical correlations between the particles. So ideal gases have no correlations because everything is just flying around and nothing sees anything else. But interacting gases, the particles see the other particles. And if I have a particle over here, then I can work out what is the probability that there'll be another particle a certain distance away, and then I can work out what is the force that that particle exerts on my original particle. So the effect on the pressure is going to be affected by the way that the particle positions are correlated. And so we're going to have to define what we mean by correlation and show how that then actually influences the pressure. So that's the picture that I want you to, the verbal picture that I want you to have in mind, because I'm going to do calculations that are quite maybe quite well, they certainly will be quite involved very shortly, and so I want you to have that picture in mind so you know what it is that we're calculating when we're doing this. So I want to just introduce then what I mean by correlation function. So I'm going to be talking about correlations, and in particular, I'm going to talk about the thing called the pair distribution function. And sometimes it's called a radial distribution function. So, so the basic idea is that in an ideal gas, the atoms, the particles, are completely independent. And so that means that if I want to know what is the probability unit volume of finding another gas particle the distance r from a particular one, that probability is independent of r. Okay, so the ideal one is like this. Here's my gas. Here is a particle that I'm interested in, and I want to know what is the probability of finding another particle, say at this point over here. So that's what I want to know. What is that probability? And the answer is for ideal, P is independent of this vector R. Because the particles don't even see each other. So it's just a constant. The probability per unit volume is just the probability of finding another particle in that volume. That is just going to be 1 over the density. So that's what you would expect for an ideal gas. And for a non-ideal gas, since the particles interact, which means they have an energy that depends on their separation, so therefore P must depend on R, and those, and so therefore the probability, which I'm calling P, really bad idea to call it P when I'm going to also use the pressure P. So the probability P, I don't know, let me call it PR for probability. So then it looks like that. Okay, so that's what we're going to try to calculate. So let me start off then by showing you how we can use the virial theorem to calculate the equation of state of an ideal gas. So the goal in this section is calculate the equation of state for ideal gas using the virial theorem. So this is going to be the simplest derivation of this, the most economical and the most interesting one of all the derivations that you've seen in this class. You've seen multiple derivations in this class. This one really is quite mind-blowing. So we're going to define the virial, as I said before, as the expectation of the sum from I equals 1 to 3n qi pi dot. So that's how it's defined. And we know that Newton's second law says that pi dot is equal to the force, component of the force. So therefore I can write this as the sum from I equals 1 to 3n qi fi. Okay. All right, so now let's draw a picture to see what forces that we are interested in. So here is the wall of the container, and I have my particle coming in like that, and it's coming in, transferring some momentum to the wall, and so that momentum will be a force, and is going to be in this direction. So that's going to be the force, and the particle is coming in with some momentum and then leaving with some momentum. And then I'm going to say that if I want to compute the pressure, the pressure is force per unit area. So I'm going to be looking at a unit of surface area that looks like this. So this is an element of surface area on the wall of the container. And so that means that if I want to measure what is the pressure, well, the pressure I feel is the pressure that is in this direction. So that's the pressure. So that means that the force is equal to the force from particle I is minus the pressure times the element of surface area that it is exerted on ds. So and I'm writing down here that the coordinate qi is a component either x, y, or z of the position of the particle Ri. So just to make sure everybody understands, in this notation here, I represents the number of particles now. Not number, particle label. So when I use the word Q and P, I'm using it as one of the three components of position and momentum of particle I. So I didn't specify that super clearly, but I want to make sure you know that. Okay, so why is that important? Well, it's important because I can now write down what this means. So let's have a look and think about what this really means. So I equals 1, 2, 3n. It's 3 times, because I have 3 components for each particle I. I'm looking at the force in each of those components. So I claim that this thing is equal to the following. So this is an element of force. Exerted on the little element of surface area, ds. So therefore, this thing looks the same as this. It looks like the integral around the surface, and then this q, this thing then becomes r, so it looks like r, and then the force is p dot ds, so it's p dotted with ds, but there's a minus sign because of the direction of the force compared to the pressure. So the pressure is defined to be minus the force in this direction. So that's just the way pressure is defined. So then the pressure is just a number that just comes out. So this is minus the pressure times the integral around the surface of R dotted with ds. So let me just make sure you know what I'm integrating over. So here is my container, and I've got my particles inside, and now we're doing the integral over this surface. So that is the surface area for this container with volume V. So that's what we're doing. Okay, so that's the first thing. I've turned the sum over I QIFI into an integral over the surface. So that's the step that's harder. You have to see that this Q then turns into this R, and this F turns into this PDS. So that's where that equation comes from. Okay, now here's a trick that's really cool. So the math trick to make this work is to use the divergence theorem. Okay, you remember the divergence theorem from simple vector calculus? So the divergence theorem says that this integral of R dotted with ds is equal to the integral, this is over the S, is equal to the integral over the volume of the divergence of R, and then the integral V. So that's the divergence theorem. But what is div R? Three. Thank you, Andrew. Because it's dx by dx plus dy by dy plus dz by dz. So this is just equal to 3. And so now what I've just shown you is that then the virial is equal to minus 3 times the pressure. And then the integral, this then is equal to 3v. So now I've got the integral is equal to virial is equal to minus 3 pv. But I have the virial theorem, which says that this is equal to minus 3 n kbt. So this is from the calculation. And this is from the virial theorem. And so that means then that PV equals n kbt. And that's the ideal gas vol. So isn't that cool? Isn't that easier than doing delta functions and stuff? Okay. Any questions?
Can you explain again the part where you said the force vector is equal to negative pressure times the area element?
Yes.
Right.
So pressure is force per unit area. So let's suppose that I'm looking at the force exerted by the particles that comes in like this and hits the wall. Okay, so I've got a little bit of surface area, and a particle hits that little element of surface area and creates a force, and the pressure associated with that force is then the force divided by the area, which is ds. So therefore the force is then the pressure times ds. And the force is the rate of change of momentum of that particular particle. So that's true for one particle just hitting the wall like this and bouncing off. Now I want you to imagine averaging over the whole wall, and there's lots of particles coming in all the time, and so we can sort of average the force and therefore get the average pressure. So there's a sort of very subtle coarse graining step there, which I didn't explain until you asked me to explain it. So, but did I answer your question?
Yes.
Right. So what I want to say is that this step here is the clever one, and going from here to here, this is discrete particle impacts. And then this on the right-hand side is the coarse-grained pressure. So you can see there's a pressure, but it's just one particle hits it, there's a delta function in pressure. Averaging over all the particles hitting the wall, then you get this average pressure, which is the thing that you actually measure. So the point is that the variable pressure is a coarse-grained variable averaged over many individual particle collisions with the wall. So in that respect, it's sort of like the density being a smooth coarse-grained variable, as we discussed at the beginning of the class. Okay, so did I answer your question? Yep, okay. All right, so now so that's great. So now let's talk about what happens with a non-ideal gas. So with a non-ideal gas, there's going to be two contributions to the force of the change of momentum. So one contribution is going to be the wall, the collisions with the walls. But the second one is the interparticle forces from the two-body interactions between the particles. And what we're going to assume is that those two particle forces, which in principle depend on Ri and Rj, we're going to assume that they are central forces, so that they are forces that depend on the distance between the particles, and we're going to assume that they just depend on the radial distance. So we're going to assume it depends on the absolute value of Rij, and that's the interaction between particles I and j. So to write down the full the full interaction, we have to remember that the Hamiltonian for the system is then the sum from I equals 1 to n pi squared over 2m plus 1/2 the sum from I not equal to j of u of Ri minus Rj, like that. So let me just talk about this very quickly. So first of all, here we're assuming that particles don't interact with themselves. And then this 1/2, where that comes from, is particle I interacting with particle J, should only appear once. So in other words, we don't want to overcount. So that there might be a term, you are, well, I think you all understand overcounting, right? Yeah, okay. All right. So then I'm going to define Rij to be Ri minus Rj. I'm going to call vector Rij is equal to the vector Ri minus Rj. And I'm going to write down the virial is equal to the ideal gas virial, which we just calculated, plus some change delta V, and we're going to then compute the contribution from the interactions. Well, we know that the force that comes from a potential is just the gradient of u, so that's just equal to the force. So I'm going to then say, then we can write out what delta V is. So therefore delta V is equal to the following expression. It's the average of the sum over I not equal to J of Ri dotted with du ID Ri, that's the force on potential on particle I, and that depends on the distance between particle I and particle J, and then we sum over particles. We sum over particle I and J through this double sum over here. So that's the definition of what is the contribution to the interparticle forces from the two body interactions in the virial. Okay, so that's the definition. So the next thing we're going to do is I'm going to simplify this expression. And the simplification is a bit subtle, and so I wouldn't advise trying to understand every single step of it as I do it live, because sometimes sometimes it can be a bit confusing. The algebra is relatively simple, but there's a couple of steps that I'm going to do which try to simplify the form so I can beat it down into the form that I want it to do. So there's nothing fundamental about them. They're just algebra steps. So the goal then for our next manipulations is we know that U only depends on the distance between particles, Rij. So, but this formula that I have here is in terms of the actual positions of the particles. So that's what we know, but the formula is written as things like Ri in it and so on. So what I'm going to try to do now is we're going to beat it down into a form where it just depends on Rij. And that Rij is the scalar Rij. Okay, so this is how I'm going to do it. There's probably many ways to do it, but this is the way that I decided to do it. So I'm going to take this object, du by dri, which is basically the grad of u. U depends on Rij. It depends on the scalar quantity Rij. And I can write that as du by d Rij, the scalar quantity, times d Rij by d Ri, and that is a vector. And when I say d by d Ri, let me just write down that explicitly. That is the vector whose components are d by dxi, d by dyi, d by dzi. And then I goes from 1 to n, labels the particles. Okay, so that's the object I want to consider. So what I'm going to try to do is I'm going to compute, first of all, the first term. So we're going to look at drij by dri, and what I'm going to do is the following. So here's how to simplify this. So we know that the scalar Rij is the absolute value of Ri minus Rj. So that means that Rij squared is equal to Ri squared plus Rj squared minus 2 Ri dotted with Rj. So that's true. So now what I'm going to do is then I'm going to differentiate with respect to the alphath component of d by d Ri. And here alpha can be either x or y or z. So I'm going to differentiate with respect to that. So let's go ahead and do that. So what I'm going to do is a d by dri. So here's what I get. I'm going to get d. So I got r squared. So this is the quantity I'm differentiating. So what I'm going to get is 2 Rij times d Rij by d Ri, and then the alpha component, which I'll write like that. And then that is going to equal, well, let's have a look on the left-hand side there. So first of all, I'm differentiating with respect to the vector Ri. So therefore, anything with respect to Rj is just a constant as far as the thing I'm differentiating with respect to. So that thus goes away. So I've got Ri squared. So the first term I get when I differentiate with respect to that is 2Ri. And then I'm looking at the alpha component. So it's going to be 2Ri alpha. So what I'm going to get over here is 2Ri alpha. Then there's the term Rj squared. That term is going to give me nothing because Rj doesn't depend on Ri. And then I'm going to get the last term, 2Ri dot Rj. So I take the dot product and then differentiate with respect to the component of Ri. And so what I'm going to get there is minus 2 Rj alpha. So when I differentiate with respect to the alpha component of Ri, because it is in the dot product with respect to Rj, it's linear in that, so I just get a constant, and then I get Rj. So this thing then is actually 2 Ri alpha minus Rj alpha. So you tell me what is alpha, x, y, or z, and then I've got that. And so now I can write this down in vector notation. The twos cancel, and so I can say then that d by d Ri of Rij is equal to then the vector Ri minus Rj, which is the vector Rij, divided by Rij itself, which is the magnitude of Rij. And so that's what we have here. Similarly, I can do this with respect to Rj. If I took d Rij by d Rj, and that's going to be the vector, that's going to be the negative of this, it's going to be minus d Rij by dri, and then that is equal to minus Rij over Rij. So I'm being very careful here to distinguish scalar quantities from vector quantities. Okay, so then I can now go back to my definition of the virial. So this means then that delta V is equal to minus the expectation value sum over I not equal to J of Ri dotted with Rij over Rij times du by drij. So this quantity here that I've drawn you, as you can see, it's basically symmetrical in I and J. So I can exploit the symmetry in I and J. And so what I'm going to do is I'm going to write this as equal to minus 1/2. And what I'm going to do is I'm going to add the two terms together. So I'm going to write it as the sum of I not equal to J Ri dotted with du by dri plus Rj dotted with du by drj. So these two terms, because I'm summing over I and j, this term here and this term are actually equal, because I and j are just dummy variables. I'm just summing over those, summing over all I, all j. So therefore, this thing inside the angle brackets is twice what I had before, and so that's why I've divided by this factor of 2 over here. But the reason I've written it like this is because now, since I know this equation and I know this equation, I can write this whole thing as equal to minus 1/2 the sum over I not equal to j of Ri minus Rj dotted with Rij over Rij times du by drij. Okay, now we're nearly there because there's two vectors up here. So this is a vector. This one is vector, and they're the same thing. So this whole thing then is equal to minus 1/2 the expectation value, the sum from I not equal to j of Rij squared, the scalar quantity squared, over the scalar quantity Rij times du by drij. And then one of those, the numerator cancels with the denominator. And so I end up then with my final result that this thing is equal to minus 1/2 the expectation value of I not equal to j of Rij du by drij. Okay, and so now what I've done is I've done exactly what I said to do over here on the left, is that I've taken my formula for the virial and written it down into an expectation value of a quantity that depends only on the magnitude of the distance between two particles I and j. Okay, so okay, so that's fine. So that's fine, but so what? And the answer is this object is actually related to the correlation function. So what I'm going to have to do now is I'm going to show you that. So I'm going to define what I mean by the correlation function, or in this particular case, the pair distribution function. So I'm going to define that, and then I'm going to show you how this object is related to that. So let's now talk about correlation functions. So the thing that we're really going to talk about is the 2-point correlation function. And what we're going to be looking at is the probability of finding two particles separated by a vector r in thermal equilibrium per unit volume. And we're going to call this object G of R. So let's write down what it actually is. So let's suppose I have a volume V. Here's my system. So it's a volume V, and in it I've got a bunch of particles. So there they are. And then you tell me what is your vector V. So you might say, okay, the vector V I'm interested in is two particles that are separated, the vector R rather, not V. The two particles are separated by this particular vector. So I take this vector and I move it around in the volume. I stick one end of it at every single particle, and I see, is there another particle a distance R away from it? I count the number of times that happens, and that then will enable me to count how many particles there are in that volume that are separated by that distance, and I can divide by the volume to find the probability per unit volume. Yes, question.
You probably covered like exact distance.
I'm going to cover it, yes. So in reality, we're going to be talking about the probability for the distance between R and R plus dr. Okay. So we're going to compute a probability density. But literally what I'm going to do is I literally put the tail end of this vector on every particle and see if the other end reaches another particle, I'm going to count how often that occurs. So that's sort of what I'm going to do. So let's count how many particles are separated by such a distance. By this r. So the answer is, well, what we're going to do is we're going to sum over all pairs of particles. So I is not equal to j. And then what I'm going to do is I'm going to say, take the position of particle I, take the position of particle j, look at the distance, but look at the vector between them, and then see if that equals the thing that you want, r, and then stick a delta function around that. And if I stick a delta function around that and sum from 1 up to n, then that's going to count the number of particles separated. So this number, if you want, is equal to this. So the idea is that the delta function is equal to 0 unless the two particles are separated by the right amount, in which case it is a 1 or an infinity if I'm averaging. Then I'm going to, so this is just true for a static snapshot, but I want to do this in thermal equilibrium. So I need to average by putting thermal expectation value brackets around this. So I have to do this in thermal equilibrium. And let's have a look at how we could simplify this. So in doing this, I've counted many different particle separations. How many particle separations have I encountered? Well, in this sum here, there's the number of terms is equal to n for I, and then j can't be equal to I, so that's times n minus 1. So there's n times n minus 1 terms. And so if I want to know what the probability is per unit volume, so I'm going to call that G of R. I'm going to divide by the volume. The answer is going to be this object divided by how many times I try to estimate this, which is n times n minus 1. And so that's how I'm going to define my distribution function G of R. Okay, so then what I'm going to do is now I'm going to do a trick, and the trick that we're going to do is one that you'll see theorists do quite often. So we're going to do a trick. We're going to write the number 1 in a complicated but clever way. So I'm going to do that, and then I'm going to stick that, substitute into the formula the delta V. So that's the thing that's going to come next. So let me show you this. So let's first of all write down the trick. So if this is true, so you all know that if I have if I do an integral over space of delta of r minus a times f of a, then that is equal to, sorry, f of r, and that is equal to f of a. And that's also true, of course, if I wrote down integral d3r delta of r minus a times f of a, that's also f of a. Because the integral of delta of r minus a, that is equal to 1, and that's just a constant. So we just get that. So let me make this crystal clear here so that we don't get confused. So that here is meant to be an r. Okay. All right. So then I claim that then I can write 1 in a very complicated way. So I can write 1 is equal to the integral d3r of delta of r minus ri minus rj. So that has to be true. This ri minus rj is the following. You tell me what I is, you tell me what j is, you tell me what therefore what ri minus rj is. It's just a number. So this thing here, this ri minus rj, is kind of like this a in the formula above, and so that is equal to 1. Okay, so that's definitely a true statement. So then what I'm going to do is write down now what the virial is. So therefore the virial, or the change in the virial, is equal to minus 1/2 times the expectation value of the sum of I not equal to j. And then I'm going to put in my complicated way of writing down 1. So integral d3r delta of r minus ri minus rj. So that's my complicated way of writing that down. And then I have the rest of the formula, which is my rij times du by drij, and then close the angle bracket. So that's what I have. And why is this nice? Because now that I have this formula, so this thing over here, this thing here is of course the vector rij. And because it's the vector rij, I can now replace everywhere where you see rij, I can replace it with r. Okay, you may say, well, why would you want to do that? So let's have a look and see what happens. So then I claim that then this thing, that the virial is now going to be minus 1/2 the integral. No, let me do this in one extra step. So sum I not equal to j, and then the integral d3r delta of r minus rij, like that, as I had before. And then over here, I'm now going to replace this as r du by dr. Because I know that this delta function is just going to replace r by rij. So I can just do that. So all I've done is I've replaced is I've used this result here, this second result here. I've just done that. Okay, so if that's true, then why do I want to do that? Well, that means that I can then take the r du by dr outside of the summation sign, because it doesn't live inside the summation sign, because it doesn't even depend on the variables in the summation. So now this thing does not depend and so I can now write this whole expression as equal to minus 1/2, and then I'm going to take out now the whole integral. So integral d3r, and then I've got r du by dr, So you tell me what the potential is, 1/R6 or something like that. And I've just got that function that just goes in here, R du by dr. And then the only thing left inside the, which depends on the particle positions, is the expectation value of sum over I not equal to j of delta of R minus Ri minus Rj. And this object over here, well, you've seen that before because it's the same thing as what I have over here on the left-hand panel. That thing is the 2-point correlation function. So then this thing is that this delta V is now equal to minus n times n minus 1 over 2V times the integral d3r r du by dr times the 2-point correlation function, the pair distribution function. And that's it. Ooh, excuse me, sorry, I'm allergic to neat algebraic derivations. Excuse my allergy. So then n is always going to be very much larger than 1. So therefore, I've just derived for you that delta V is equal to basically minus n squared over 2V times then the integral d3r, r du by dr g of r. But r, remember, is the system is completely isotropic, just depends, just a gas floating around. So then I can do the integral as 4 pi r squared dr. That's my d3r. And then I have r du by dr. And then I have g of r. And so in the end, what I end up with is that the virial is equal to the ideal virial, which we calculated earlier, minus 4 pi n squared over 2v times the integral from 0 to infinity of r cubed du by dr g of r dr. And this whole thing has to be equal, because of the virial theorem, which is exact, minus 3n kBt. So remember what V ideal was. V ideal was just the PV, it was just PV. So therefore, putting it all together, so now what I have then is that PV is equal to n kBt times 1 minus 2 pi little n over 3 kBt times the integral from 0 to infinity of r cubed g of r du by dr close the brackets. And by n, I mean n over v as usual. And so that's our final result. And this is absolutely fantastic, because what it means is I can go and measure the 2-point correlation function, g of r, by doing a scattering experiment, or I can do a calculation using diagrams and all sorts of things like this. And once I've done that, now I can work out the equation of state for my interacting gas. So one more, so that's the, so some quick comments. So this is this is a formally exact result. For central potentials. Where the potential is rotationally symmetric, so it doesn't depend on the direction. So that's the first thing, and then so it looks really great, and it comes from the virial theorem. So it's exact and all of that. Excuse me. So there's only one problem. So the only problem we don't know the 2-point correlation function or the pair distribution function. Okay, so you say, well, okay, well, maybe we can fix that. Maybe we can calculate that in some way, and then we can then have an answer. So let me tell you. So what we're going to do next. So I'm going to show you a quick and dirty trick for calculating G of R. Okay, just to give you some feel for it. So we'll do that. There is an exact way to calculate G of R. So you can actually calculate it. It's really good. So you look at the 2-point correlation function, the probability of two particles being a certain distance apart, and you can calculate it exactly. The only thing is you can calculate it exactly in terms of the 3-particle correlation function. The probability that a particle here and a particle here and a particle here are certain distances apart. Okay, so then you have to calculate the 3-particle correlation function. And you can calculate that exactly too. But you can only calculate it in terms of the 4-particle correlation function, and so on. So in every field of physics, the whole reason the problem is hard is because of this problem of closure. That you can write down a formula for anything you want to calculate, and it will usually be, at least if if it's the sum of pair potentials, two particle additivity, you ignore 3-body interactions in the energy, just in 2-body. It's usually just going to be in terms of the 2-particle correlation function, but the 2-point correlation function depends on the 3-particle correlation. 3-particle correlation function depends on the 4-particle correlation function, and so on and so forth. And that problem is called the problem of closure. It's why we can't do many-body theory exactly. It's why we can't solve turbulence exactly. Why we don't know how the brain works exactly. Every problem of anything interacting, the reason why it all goes wrong is because of this problem right here. So we don't know the 2-point correlation function, and we can calculate it if we know the 3-point correlation function. But the 3-point correlation function can only be calculated from the 4-point correlation function, and so on ad infinity, ad infinitum. So all of theoretical physics in many-body theory and statistical mechanics, electronic structure of materials, fluid mechanics, everything. It's all based on trying to find ways to get around this problem. So this problem is called the closure problem. And that closure problem is can be roughly stated as follows. We always have one more equation. Then we need, so we can't calculate anything. At least exactly. And so that means that we have to do approximations. Now, there are some problems where you can solve the closure problem. There's various statistical mechanical models and so on, which we know where you can solve it. I'm not going to go into that. There's people who spend their whole careers just working on this problem, and their expertise is knowing how to solve that problem with one particular system. Okay, let me wrap up by I want to write down a formula for the 2-point correlation function, the pair distribution function, in a slightly nicer way than the way I've written it down. So I want to finish with that. So that's point number 4. So point number 5. Here is a simpler way to write the 2-point correlation function. I'm used to calling it 2-point correlation function, but the way we've implemented it here, it's really the pair distribution function. And the simpler way to write it is I want to get rid of all these sums. So if I were to write it down back from its definition, so it looks like this: V over n minus 1 times the sum I not equal to j delta of r minus ri minus rj. So that's what it is. Close that, and then what else do I need? I need angle brackets, so I'll put those angle brackets in there like that. So that's how we defined it. And what I'm going to do is I'm going to say the simplification that we can make is we're going to, so these are dummy variables. So let's choose I to equal particle 1 and j to equal particle 2. Okay, then what I get for particles 1 and 2 when I average over them is going to be the same as for any other particles. So therefore, I can then write this thing as the sum over I not equal to j, that's n times n minus 1 terms. So the n times n minus 1 are cancelled, and then I'm going to get v times the following. The integral, I'm going to write down all the variables explicitly for you, d3r1, d3r2, all the way up to d3rn. And then my thermal expectation value, so that's has a Boltzmann factor in it, e to the minus beta u. Then I have my delta function that says r is equal to r1 minus r2. And then I have to normalize it by the expectation value. So then that's normalized by integral d3r1 up to d3rn, and then my Boltzmann factor, go away, my Boltzmann factor, e to the minus beta u. So it looks just like that. Okay. And the kinetic energy is just, as we saw, we can always integrate out the kinetic energy exactly. So that's just the Gaussian integral. So the kinetic energy is just some number, which is like the Fermi de Broglie wavelength to some power. It's the same in the numerator and in the denominator, and so it cancels out. So in all of these statistical mechanics problems, all we're dealing with is the integral over the potential energy, or what we call the configuration integral. Okay, so that's sort of much easier to deal with. So we can just do that. Okay, so we're going to take a break now for 10 minutes, and then at 3:30 we're coming back, and then we will have our makeup lecture. So I'm going to stop the recording, and we will